Okay, so let's go to the definition of orbifold. So we begin with the Hausdorff second countable topological space. So let n be a fixed number, and so we take an open subset U tilde in Rn with the finite group G acting smoothly on it. G invariant map U tilde to O for an open subset of X, inducing a homomorphism from this quotient U tilde ma G to O. So the orbifold chart is such a triple. So U tilde G and phi. So given two of these, V tilde H psi is another one. Then it is so you want to understand what embedding means is a smooth embedding of this U tilde V tilde with phi equal to psi circle I, which induces the inclusion map for U, which is the image of U tilde, and V, which is image of V tilde. So these are all in X. So equivalently, I is an embedding inducing an inclusion map, and inducing an injective homomorphism I star G goes to H such that IG circle G is I star G circle I for every G in G. I star G will act on open set, that is the image of I. So here, of course, this is equivalent, but the proof is not really, proof is a bit hard, and it's probably in the paper of Moedzik. So we will but skip that. So note that I can be changed to H circle I for any H in I, and the images of HI will be destroyed for the different representative of H mod I star G. So however, these H are sort of undetermined here, so you can always change this I with some H circle I, and it is equivalent to equivalent definition, whatever which one you use. Okay. So two charts U tilde psi and V tilde phi and U tilde phi and V tilde psi. So I omitted the group here. Are compatible if for each x in U intersect V, there is an open neighborhood with W on in of x in U intersect V, and the chart W tilde K mu such that there are embeddings to these models. So there's from this chart there's always embedding. So we can assume that W is a chart of V intersect V here, U intersect V here. So if we allow U tilde to be open subset of closed upper space, then the orbifold has a boundary. Again, these so again the points corresponding to X. So the boundary of this upper half space corresponds to boundary of the orbifold. Again, the proof uses the invariance of domain theorem for this to work. Again, the boundary is a well-defined set because of the this invariance of domain. Okay. So since G acts smoothly, G acts freely on open dense subset of U tilde. So this is follows from the smoothness, and we covered it because if you have a locally smooth action, this is always true. So this was in the Braden's book. So orbifold atlas of X is a family of compatible charts covering X. So of course I am omitting G group here. So two orbifold atlases are compatible if charts in one atlas are compatible with charts in the other atlas. So this set of atlases form a partially ordered set. So by the inclusion relation, and of course it has a maximal element by the Jones lemma. And given an atlas, there is a unique maximal atlas containing it. Okay, so orbifold is X space X with the maximal orbifold atlas. Okay, so maximal orbifold atlas is what we mean by here. So one can obtain an atlas of linear charts only, that is charts where U tilde is an Rn or the upper half space, which I with boundary, which I said above, and when we want to talk about the boundary. And the G is in orthogonal group. That is, for each point we can find the subgroup Gx stabilizing the point and suitable Gx invariant neighborhood in it. Then the Gx acts linearly up to choice of coordinate charts, because smooth actions is of course locally smooth, as we saw in the Braden's book here. Okay, so we can always find these atlas with linear charts. So if you have u tilde with G acting freely, then we can drop the atlas from the atlas and replace with finite in many charts with trivial group. So that's again very easy. And so if you have a orbifold xu and yv, then the map is smooth if for each point x and x there's a chart u tilde g phi with x in u, and the chart v tilde h psi with f. Sorry, this is psi x in b, so that the psi x, fx is in b, not psi, sorry, fx is in b, and then fb is in u, and then f flips to f tilde u tilde v as a smooth map. Okay, so that's the definition of smooth map. So if you can do that for everything, but of course there's some ambiguity about the lift. So lift can be different, but the smoothness doesn't really make any difference there. So two orbifolds are diffeomorphic if there is a smooth orbifold map with a smooth inverse orbifold map. And x is in x, then the local group can be defined. So local group gx of x is obtained by taking u tilde g phi around x and finding the stabilizer gy for y inverse image point of y. So this gy is not only defined up to conjugation, because you can choose a different inverse image point. Okay, so it's not well defined as a subgroup of G, but only up to conjugation. But it is actually it is independently defined up to conjugacy for any choice of Y, and so it's also chart independent, because if you choose a smaller chart, then you will give you the same conjugacy class, because so whatever chart you use for X, this model action will be the same, because one can take a linear chart, and once a linear chart is achieved, then the Gx is well defined up to conjugacy there, and whatever chart that contains it will have the same stabilizer, okay? Because the action is basically feasible. So as an abstract group with action. So Gx is well defined as an abstract group. So the local group is well defined. So the singular set is a set of points where Gx is not trivial. So the subset of the singular set where Gx is constant is a relatively close submanifold. So relatively close means that for each point you can find a neighborhood where the intersection is a closed subset. Closed subset, that's the what relatively close means. So this is a very good fact, because you can sort of prove this using the linear chart, because in the linear chart, so where the Gx is constant is easily shown to be some linear subspace, so you can use that fact. So using this fact, so X becomes a stratified smooth topological space where star is given by the conjugacy classes of Gx. So so here I didn't really define what stratified smooth topological space is. We will define this shortly. And stratified just means that it is a union of smooth topological manifolds where the and then you use some type of weak topology, and there's some tubular neighborhood condition there, but we will talk about that later. So so now we define what suborbifold is. So suborbifold y of x is an embedded subset such that for each y in y, there's a chart for x in the neighborhood v of y. So this is a neighborhood in x, where there's a chart for y for this suborbifold y given by p intersect p comma g but p psi. So this is a restriction of psi to p again. where P is a cross submanifold of B tilde where Gx1 and Gp is the image of the restriction homomorphism of G to P. So the group has this. So G mod P is may not be a monomorphism, but you still have to restrict it to this P, and then you get another group. So in Adam, for example, they require this restriction homomorphism to be injective, but we do not require that here. So that's what I did differently from them. So we go to example. So manifolds are orbifold because it has a Euclidean labeled cover where the groups are all trivial. And if let G be a finite group acting on a manifold M smoothly, then M mod G is a topological space with an orbifold structure. So here, of course, the orbifold chart will be given by the original chart of M, whose image is in M mod G. And then, so if G has some fixed point, then you can find the local chart where G acts non-trivially and has a fixed point. So you can define this kind of cover when you have this finite group action. So for example, let Tn be MBTN and G acts on it with a generator acting by minus identity. So for example, what I mean by minus identity is that the Tn is, you can think of it as a Tn as Rn mod Gn, and then this minus identity will induce a map. So for n equal to 2, then then M mod G is a topological, G2 is a topologically a sphere and has 4 singular points. So here what happening is that you can kind of think of it as M as a circle times circle, and G2 acts by rotate. So you embed it in the standard way, and then the x-axis passes through the 4 points, and then you do the involution and take a quotient. Then it will be a sphere with 4 singular points. So this will give you an example of orbifold. And for n equal 4, we obtain what you call the Kuma surface with 16 singular points. So in general, you can do it for every n, and then these will all give you orbifolds. So let's go to another example. So let X be a smooth surface and take a discrete subset. So for each point, take a disk labeled D with the chart D prime Gn Q, where D prime is a disk and Gn acts as a rotation with O as a fixed point, and Q D prime goes to D as a cyclic branch covering. So from this surface, for this point, you remove all the atlas that containing this point, but you introduce this atlas. Okay, so then this becomes an orbifold atlas here. So this will give you an orbifold structure. So also given a manifold with boundary, then we can double it as a manifold and obtain a G2 action. So you have a smooth manifold with boundary. Then if you double it, then it's still a manifold. You can also get a smooth structure because you have some sort of tubular neighborhood here where this G2 acts. So of course the G2 action is just given by sending the point to the double points, and if the boundary, it will be fixed point. So then this has an orbifold structure obtained by this G2 action at the boundary, and every other point you just use the ordinary chart. And another thing is you can take a surface and make the boundary to be a union of piecewise smooth curves with the corners. So the interior will be just given the ordinary Euclidean chart, and the interior of the boundary curve is given chart with G2 as a group. So this is called the silvering. So you are making these into mirror points. And the corner points is given by charts with dihedral group action. So if you have a corner, so the corner in this sense will be just the product of two open intervals with the half open intervals, you obtain some kind of a, or you can just use the non-negative x-axis, and then you take the product, and it will give you a corner or the quadrant. So every point will be modeled on that set. So corner point will be the ones corresponding to the corner, and then you can give a dihedral group action as a group in this chart, because so if you look at the dihedral group action on R2, then you see that you can find a neighborhood which will model some corner smoothly. So you can always give this this kind of structure there. So embedded arc in the surface orbifold as above, ending at 2 silver boundary point is a suborbifold. So let's take a embedded arc ending at 2 silver boundary point, say transversely. So this is called the neatly or nicely embedded manifolds. And then if the if this ending is so that it's invariant under the G2 action in the so the inverse image in the model neighborhood is G2 invariant, then you can say this is a suborbifold. So I'm repeating the same thing as take a surface, and then you can make it into so the boundary to be piecewise smooth curve with corners, and you give a G2 action in the interior of the arcs. Then vertex can be given dihedral group action, and so union of the so maybe you don't give all the arcs these G2 actions, so all the interior points. Then the interiors of remaining arc is a boundary of the orbifold. Okay, and nicely. So these boundary of the orbifolds are non-singular points because the group itself is trivial. It's only modeled on the upper half space. So this will be the interior of the remaining arcs, and of course the mirrored parts will be not singular. And nicely embedded arc ending at a corner may not be suborbifold. So if you have some arc ending at corner may not be suborbifold unless it is the boundary of the surface, or at least it agrees with the boundary of the surface. Okay. That's because of this. So in the inverse image has to be smooth arc in the model neighborhood. In the model neighborhood, the inverse image of this arc has to be invariant under these actions. So that's why it may not be the suborbifold.